All right, welcome, kids. We're going to give this a shot. We're just going to use my phone microphone because it works a lot better due to the testing yesterday. I'm going to start recording almost everything. So in case you miss, you can just go online to this one page I'll show you. Well, I haven't made it yet, but please still come to class because I'm not quite as good on video as I am live. I mean, and I look pretty fresh, eh? Brand new shirt. You wouldn't be able to tell that on video, right? All right. How many of you thought there was a test today? Raise your hands. Okay, just two of you. Well, a week ago there was a test today, but then over the week, and I should have told you Friday. It would have been on chapter 1. Let's talk about what the test would be on real fast. Thank you, Mr. Roberts. Actually, at the end, I'll tell you what's on the test because I don't want to record it and broadcast it, and then you can just pause it and read the test the whole time. Sound good? All right. Now, today also, for the last 15, 20 minutes, we'll let you go and mass your stuff. Remember, you have a lab. You got to find the masses now that everything's evaporated. The test is 11 questions of free response or of multiple choice and 10 free response, if I remember right. There's a little bit of writing, but it really isn't too bad. All right, so let's pick it up here on units of measure. Today, it's not hard, but it's a little bit tricky, some of the things that we're going to talk about. So units of measurement, these are just some things we're going to use in this class. They're super complicated. We have mass, length, time, temperature, amount, electric current, and we never use luminosity, intensity, but whatever, luminous, intensity. You'll learn a lot more. The only thing that might be new to you is this word Kelvin. That measures temperature. We'll talk about that in a few minutes. And then this word mole, and that's an amount of something, just like the word dozen would mean 12 of whatever you're talking about. A mole would mean a huge number of whatever you're talking about. Easy enough. Current is an amp or ampere. Candela. We never use that in this class. You use it in physics probably. And if you ever wonder where SI came from, it's from this French system, international, the units, whatever. All right. They use a different base for each thing, and then we just put a prefix in front of that base to change it. All right. These are the prefixes. You should have the basic ones memorized, but you don't need some of these other ones like femto, pico. Those are more physics. Same with the giga. You should just know the King Henry doesn't like chocolate milk or whatever the saying is. If you really need to be able to go from kilo to milli and be comfortable with that. Who is comfortable with that already? Okay, because I don't really teach it much. There's the staircase. Who uses the staircase in their head? Anybody? Okay. If you need help on that, go online. I have resources for that. But if there's a kilo big, milli small. We do use nanometers in this class, so that's 10 to the negative 9. Easy enough. That's the weirdest way to hold your face I've ever seen, Kraus. How do you even do that? That's bizarre. Okay, sorry. That's a good word. This little thing right here is called a mu. We will use mu often in this class, and you'll use it in physics. What is good physics? Anyone remember? Anyone know? Anyone had physics? Okay, that would be why. Mu is the coefficient of friction. And if you're a real savvy person, there's a few like really nerdy T-shirts that'll say without mu nothing would work or something like that. And it's saying without friction there wouldn't be anything They're not fun, I guess, but whatever. Okay, volume, that's the liter or milliliter. A milliliter is defined as a centimeter box. So one high, one across, one deep, and it's how much water would fit into that. So a milliliter and a centimeter cubed are the exact same thing. Who's okay with that? Okay, that's literally the definition of a milliliter, the amount of liquid that would fit into a 1 cubic centimeter box. Okay, a liter is a cube 1 decimeter long on each side. A milliliter is a cube 1 centimeter long on each side. I wouldn't worry about knowing that, but that for sure. All right, this is the main part of today. Like, as far as units, you need to attach them to whatever you're talking about. So if you're measuring temperature, put Kelvin in this class, or Celsius, depending on what the problem asks for. Mass in grams or some sort of prefix and then grams. Length, same thing. It's meter or some sort of prefix attached to it. Now, uncertainty in measurements. Nobody likes this kind of stuff, including your teacher. I find its value, like I understand it, but it's not very fun for students in high school. How about that? It turns out, depending on what device we use to measure stuff, our numbers need to be reported so we know how accurate the device we used was. That's all that this idea of significant figures is. It's our way of telling the number reader how accurate the measuring tool I used was to get that number. So here we go. Different measuring devices have different uses and different degrees of accuracy. So which one of these would be the least accurate? Any guess? No, the pipette will be the most accurate. You can't see it, but there are marks on that one. The syringe and the pipette will be the most accurate. It's this flask. This flask has one total line on it, and that's it. Now, it'd be really good. Let's say that, and you can't see it. You can't even probably see it up there. But let's say this line was at 100 milliliters. It would be fairly accurate at measuring 100 milliliters, but nothing else. Okay? There are no other marks on it. The pipette, and maybe you were right. Maybe this doesn't have marks. I thought it did. It wouldn't be super accurate if it's not marked, but generally when they're glass ones, they are marked. The syringe will be the very most because it's pretty small and has lots of marks. And then these two, well, this goes to the 10. If you look at it, this goes by the 10s. So least accurate, then next, then next, then next, then next. All right, and you don't ever have to identify those, but just kind of think through it. The smaller it is and the more marks it has, the more accurate it is. Okay with that? All right, and we'll get back into that. I don't know why that's going in this order, but whatever. That's how they came. Temperature is a measure of the average kinetic energy of the particles in a sample. All right, pretty simple. In scientific measurements, the Celsius and Kelvin scales are most often used. The only time you would ever use Fahrenheit is probably in Chapter 1 when it asks you to do a conversion from Fahrenheit to Celsius or to Kelvin. But it's completely useless. We will always use Celsius and Kelvin. And they're honestly pretty much the same thing. Celsius has a 0 where water freezes. That 0 is 273.15 degrees Kelvin. Absolute 0 is 0 Kelvin. And so Kelvin's actually known as an absolute scale, while Celsius is known as a relative scale. What's Celsius relative to? Water. It's based on the properties of water. Now, since Celsius is a relative scale, it has something that Kelvin will not. So when you write like 20 degrees Celsius, you'll put a little thing up there, right? When you write 20 degrees Kelvin, I won't mark it wrong, but there technically is no circle on a Kelvin. The circle means it's relative to something, and for this, it's water. All right, Kelvin doesn't have this because it's an absolute scale where 0 is really a 0. You can't go under it. Are you okay with that? Absolute 0 is the temperature at which all motion ceases. All right, there would be absolutely no matter moving around. At 0 Celsius, there's plenty of stuff moving around. Know the following. Just memorize them. 273. And you can put the 0.15, it doesn't really matter. Kelvin. That's 0. Yeah.
So at 0 Kelvin, would time cease? Because
Time doesn't consist of matter, but the way we tell time might cease. But I think time would still pass. That's a good question. All right, so that's 0. Room temperature is considered 298 degrees Kelvin. So if it ever says that an experiment was done at room temperature, 298 K, or what's the difference between these two numbers? Is everyone okay that triangle means difference? Okay, triangle means final minus initial, or just your change. The difference between these two is 25, right? So room temperature is 298 K or 25 degrees Celsius, which is roughly 70 degrees. So almost to the exact number right now. Now it's too dark, but it was 70 point something when I walked in here this morning. All right. I just said that. That's based on water. Something that's really, really convenient and simple. Where is it? Is the fact, that the difference of Kelvin is equal to the difference in Celsius. So a change in 1 degree Kelvin is the same as in 1 degree Celsius. You okay with that? It has a different base where you start, but the fluctuations are exactly the same. Now, we would not say this for Fahrenheit, right? It's 9/5 or 5/9 conversion, which is a dumb conversion in this world, but whatever. All right. The Kelvin is the SI unit of temperature. We'll use that in most math equations that we're going to do. It's based on the properties of gases. There are no negative Kelvin temperatures. So if you're ever doing a PIV-NERT, which you'll learn later, or you're doing any calculations that involve Kelvin and you end up with a negative value for Kelvin, then you've done your math incorrectly. Are we all right with that? Are you researching whether time stops at absolute 0?
yeah.
What do they say?
Absolute 0. Right now it's talking about what it converts to on the Fahrenheit Celsius scale.
Okay. Well, enjoy your reading. All right. K, it's very simple. It's equal to Celsius plus 273.15. That is a number I do expect you to memorize from this moment on. That's 273. That was easy for me because that was my sister's prefix on her phone number. Not your sister's, most likely, unless she lives in Holiday, Utah. But 273, piece of cake. 298, hopefully easy enough. If you don't remember that, that's fine. Just remember to add 273 to whatever degree they tell you. All right? We don't use Fahrenheit. It's convenient, though, that they have KFC. I'm sure that they were thinking about that as they did that, right? All right. Density, it's a physical property of a substance, which means we can observe density over and over and over, and it won't change, correct? we're going to do a little thing here in a second. Oh, you don't go that way. So we have to do this. Where is my little eraser dealio? Also known as a rag. Getting annoyed. All right. I can go old school. All right. What I'm going to teach you, you may have already learned. I don't care. This erases well, doesn't it? Boy, Frisbee golf yesterday, I can feel it. That was the worst erasing ever. I would certainly do this with any multivariable equation that you ever use. You kids will be in 1050 or calculus, and you'll still screw up solving for the m. What does m equal? D times v. Not very hard, right? What does v equal? What? Well, life sucks, right? So v equals, you take that over, then d under, correct? All right. This is what I would like you to do. When you see one of these, draw one of these little circles. I call it a Tom circle because it looks like Tom to me, whatever. And whatever's on top, you put on top. And whatever else is it, you put it down here separately. And this isn't rocket science. In order to use this, you just cover up what you want to solve for. So please look real quick. If you want density, you cover up D, and it tells you it's m over v. Easy enough. If you want to solve for volume, you cover up volume, and it tells you it's m over d. And if you want to solve for m, you cover that up, and it's d times v. Now, why would I have you do this when you can just do that? This requires less thinking. And in AP Chemistry, when you are in a hurry and you're doing stuff, think less and just act more. Okay? Is anyone in physics right now? In physics, they're going to teach you 100 of these type of equations. Circle them like this, and you won't ever screw up, because you're going to have a test where you're going to use F equals ma, and then A will go into 1/2 mgh or whatever it is. Anyway, you're going to have multiple steps where there's different equations. Do it. I promise you it'll save you. I'm a physics major, and this is how I got through college. All right, so anyway, density. It's mass over volume. On the test you have to do on Thursday, you have 3 or 4 questions on density. One asks you for density. One asks you for mass. One asks you for volume. Let's make sure we understand our units. If density is mass over volume, it's really grams per what? Liter, milliliter. It's whatever mass I give you over whatever volume I give you. So what's density? It's usually grams per milliliter. If it's for a gas, then it's grams per liter. All right? But really, it's whatever mass unit over whatever volume unit I give you. Okay, so let's just do a real quick problem. I'll read this from your exam. Is everyone okay with that? All right. So, calculate the volume of 65 grams of liquid methanol if its density is 0.791 grams per milliliter. So once again, calculate the volume of 65 grams of liquid methanol if its density is 0.791. Man, my short-term memory is impressive. Where's my mouse? There we are. There we go. All right, so shouldn't be too hard. Which one am I being asked for? Oh yeah, why did I write volume? Looks just like mass, right? So I'm asking for volume. I cover that up. That means mass divided by density, right? All right, so I have mass of 65 divided by 0.791 equals, I don't know, 80.1. 82.1? And what would the unit be? All right. Not super hard. That would not be correct, by the way. Nope, it wouldn't be milliliters cubed. Don't ever do that to me. You can put centimeters cubed, that's fine, but not milliliters cubed. All right, here's the actual correct answer, and we'll talk about this in a minute, but the correct answer is 82. Stupid sig figs, right? And we will talk about that. It's coming up. But do you notice that this number has no numbers after the decimal? Your answer can't be more accurate than the least accurate answer. It must be rounded. So that's not too tricky. We'll talk about that. Okay, we good? I need to get rid of everything black and put like a maybe 3-foot long orange stripe on the slide advancer. I can't find anything whenever I want to. All right, next. So uncertainty in measurement. This is where we get into that idea that the things we use to measure stuff, they have different uncertainties. I'm just going to leave this screen up and just write on this. All right, where did I put it? There it is. All right, so the term significant figures refers to digits that were measured. Okay, you don't use these in math class because those are just numbers they typed on a paper. All right, they're meaningless numbers. Don't tell that to them, they'll get offended. But these are things that we get from measurements. So like from a balance, from a thermometer, something like that. When rounding calculated numbers, we pay attention to significant figures so we do not overstate the accuracy of our answers. All right, so I know it's mostly silly and a waste of time, but A, we have to do it, and B, ultimately it's not super hard, but we're going to write a number so that the observer knows how accurate the tools were that we used. All right. Well, let's just do a quick example. So let's see. Seth, will you stand for a second? All right, everyone take a guess on how tall Seth is real quick. And then write it down. 5'2", very good guess. Write down how tall you think he is. Nope. Nope. All right. See, will you stand up? You can sit, Seth. All right, take a guess on a sheet. Okay, go ahead and sit. All right, so how many of you think that Seth is 6 feet something? Raise your hands. 5 feet something, raise your hands. All right, how many people think Jesse is 6 something? 5 feet something. Okay. How tall are you? 6'2". Okay. So we have at least one. How many people put 6'2"? Raise your hand. Right? 3 people. Are we very accurate? Not really at all if only 2 or 3 people got the right answer. How come we weren't very accurate? We were just guessing, right? Within reason, we figured he was close to 6 feet. Those of you that put 5, did you put a high number, like 11 or 10? Yeah. Okay. Within 3 or 4 inches, but no one should have guessed that he was 6'2" and 3/4 of an inch. How come you wouldn't guess a fraction? It's ridiculous. It overstates how accurately you know his height, right? Would have been creepy. Yeah, it might have been creepy. All right, now, how come all of us got Jesse's foot correct, that it was 5 something? Too short, 6, and she's super not like mega short, right? All of us start with a 5, except for 2 or 3 of you, right? So we're kind of used to that, so it's a little bit easier. But we still didn't guess 5'4" and a half. All right, I do this in regular Keb, and I had Josiah Williams stand up. She's way tall. All right. She's not that tall, but it was like the best, most perfect situation. I asked 3 people, one really, really tall kid, one really, really short kid, and then Josiah. And I said, Joe, how tall are you? And she said, I'm 5'11" and 3/4. How come she can put the fraction? She knows. This is a girl her whole life with wool and has to be 6 feet tall. Okay? She knows. She's been to the ruler, and all of us have. I know that I'm almost the exact same height as Joe. Because you know why? Because my sister's 6 feet tall. And she's just a little bit taller than me, and I've hated it my whole life. Okay? We know because we've accurately measured. All right? But when we can't overstate, you don't know my height, I didn't know Seth's height. We took guesses and we were sort of close, but we wouldn't ever say a fraction. Easy enough? Okay? All right, so here we go. Here are the rules. Whoops. I'm changing something on the screen right now. First off, if the next 10 minutes does not make sense, I think the videos I made online are really good for this. There's 2 of them. It says significant figures, and then the other one says sig figs and calculations. You already watch them? Yeah. All right. Because, it was on the calendar. I know. How were they? They were pretty clear. Okay, thank you. I'm way better, honestly, at those videos than I am teaching you live because the door shuts, my prep hour, except for this year, he has the same prep. And I don't dislike Goddard, but I dislike that he never shuts up. That was on video. I never said that. No, oh man, I get so little done in my prep hour. And it's actually what you're supposed to be doing. Like, we're not like, oh, hey, how's your family? We're like, hey, how do you think we can do this better? And I'm like, I don't want to do that right now. I want to make my AP better right now. But whatever, we're good. All right, here are the rules. All non-zero digits are significant. So if it's a number besides a 0, you got to count it. Did you get the email that Friday? We just worked in there, so you didn't miss anything. Boom. That's coming up. You just had the spirit of Chem prophecy. Okay? Number 2, zeros between 2 numbers, or sig figs, are themselves significant. So yes, if you have like a 102, that O in the middle is important. Rule number 3, zeros at the beginning of a number are never significant. Those are what we call placeholders, and they're not that important. So if it's like a 0.72, that first 0 doesn't matter. And it could be 0.0000. 7.2. This rule would say there's only 2 that are significant. And what's going to get dumb is when I throw a 0 here, because that one does count. That one's really important. And look, real quick, I'll try to explain why, and some of you will just never like this. If I say there's 2 sig figs, it really means I only know that number. Because in sig fig land, the last one's always a guess. If I put a 0 here, that means I know to that number. That makes sense? So that extra 0 is a more accurate value. Yeah. It's weird. All right, zeros at the end of a number are significant if a decimal place is written. Okay, so what this means, if I just the number 100, there's only one number that's important. That's the 1. If I put a decimal right there, now there's 3. Okay, because numbers end of the number, or sorry, 0, they're not important unless there's a decimal, and then they're very important. Okay. Significant figure. All right, when addition or subtraction is performed, answers are rounded to the least significant decimal place. And then when multiplication or division is performed, answers are rounded to the number of digits correspond to the least number of significant figures in any of the numbers used in the calculation. Well, that's easy to understand. All right. Okay, there's a fairly simple little trick with sig figs to help you determine how many there are. First off, the rule will be dependent on what number has a decimal or not. So this number has a decimal, right? If there's a decimal, you draw an arrow from the left to the right until you hit the first non-zero. And then you count everything after that. So 1, 2, 3, 4, 5, 6 significant figures in that. Okay? If there's a decimal, left to right. If there's not a decimal, you go from right to left until you hit a non-zero, and then everything else after that counts. So this has 4 sig figs. Okay, and when the top rule is useful is when it's a very small value, like 0.00050008. There's a decimal, so you start from left to the right until you hit a non-zero and count everything after. I don't know, that made it worse. This is the rule that I learned when I was your age and made me get them all right. Okay? I am all about not having to think, because I'm not a super smart person, but I'm really good at figuring out ways to do stuff without having to work hard. I think that makes me a genius, right, Kraus? Even though I can't do whatever you were doing. Okay. Does that help at all? Yeah. Well, the only reason there would be zeros in front was if there was a decimal, and then you'd have to follow that rule. We don't write. If I'm going to write 200, I don't write. That'd be weird. Okay, well, we don't report dates. This is a balance, how we actually measure stuff. So, if you look here, this is a quadruple beam balance. It says that we have something that's 132 point, and then it gets a little bit trickier, but we're between 0.5 and 0.6, right? So 132.5. Then you can barely see it. If you're on a normal computer, it's easier. But this is pointing after the second one, but not before the third one. So it's a 2. But we would not write that answer. We would then add a guess. And it's pretty close to the far side, so I'm going to put an 8. But a 0 would be fine. Okay. Then I'd put a little g here. That would be the correct value from a reading here, 132.5. That's not accurate enough. Because if I just write 5, it means I know 132. But I know more than that. I knew the 5 and I knew the 2. This number is that long to show the person that reads this number that our scale was accurate to that value. Okay? When you look at something like this and you are making an observation, it's all knowns. Did we already do this? We did not? Okay, good. It's everything that you know without any shadow of doubt. With every fiber of your being, you know it, and then one more number as a guess. And that number's there to indicate that you knew all of the other ones. Okay? So this would be letter A. Let's see if you can read letter B. Or, I don't know why I said that. Let's see if you can do number 2, which is nowhere near what accidentally came out of my mouth. I know it's hard to see. Maybe I'll turn this other light off. All right, do we have an answer? Who thinks it's A? Raise your hand. B, C, D. All right, the people that raise their hand for C, they are correct. Most of you put B. Why is B almost correct, but not quite? The answer is because you know that's a 0. This would imply all we know is that's a 4. If you look, it's a 4, that's what this is, but is it past the 1? No, so you know this is a 0, so then you have to guess. Okay? I don't know for sure, but Jesse's dad is a chemist at Autoleaf still, right? He probably has to report numbers to a really, really, really specific measurement because they deal with stuff that explodes. Okay? You don't want to ever guess. So he probably has tools that measure way out here so that he can be really, really accurate. Anyone dealing in a real chemistry lab is going to have a scale like I have. It reports at least to the 10,000th place because accuracy leads to better results and less spending on expensive stuff that you don't need to do. How about this graduated cylinder? First off, you read a graduated cylinder from the bottom of the meniscus, which is like right here. Okay, just go with that. And then we'll move on. Okay, who says it's A? Good, nobody. B, C, and D. Okay, the most accurate is D. 20 is reported accurately for sig figs, but it's underneath 20, so 19.9 is a little bit better guess. Now, remember, it follows that sentence I just erased. It's all knowns. We know it's between 19 and 20, so it starts with a 19 and then a guess. There are no other lines here to gauge, so we're good. All right, that's kind of how those work. We comfortable with that? All right, I think we were on the last slide. Yep, we were. Okay, let me pause this recording because I am going to show you your actual test here. Hold on.